Actually, go ahead.
Thanks, Graham, for the nice introduction. So today we're going to cover the topics about document level models. So in most of our previous lectures, we cover models about neural networks and how they can be applied to NLP. A lot of them are kind of straightforward. So let's have a recap of what models we have. So this is not all we cover, but some of them. For example, this one is a language model, and this one is parsing. This one is actually sentiment classification, and this one is anti-tagging. So all these models are actually sentence level models. Well, in language model is a little bit like kind of document, but the element of language model is all words. For parsing, you always parsing a sentence, and for classification, mostly for sentiment classification, you classify the sentiment of one sentence. For anti-tagging, you are tagging within one sentence. This is not like strictly sentence-based, but mostly it's good to work on sentence boundaries. So actually, every little task of this have their counterpart in document. So because we have four of them, we have four counterparts, as I am aware. So for entities in sentence, you normally do anti-tagging. In terms of document, you can do some more sophisticated things like coreference. For parsing in sentence, you do semantic parsing or syntactic parsing. In documents, you do discourse parsing. And then language model in the sentence level, not exactly sentence level. I would say word level because you are going through the whole document for language model anyway. But you are doing word prediction. As we talk about language document level stuff, we can do language model on sentence prediction or discourse element prediction, something not larger than the word unit. As for classification, we can do sentence classification. In document, we do document classification. Some of this, when we transform into document, the nature of the problem changes a lot. But mainly in this course, the first three items like in the green box actually changes a lot because they're trying to recover the structure of a document. I'm not going to cover about document classification here because I'm not really aware of that. I'm not really expert of that, and I think document classification have shared a lot of similar like nature to sentiment classification, but the three other ones have very different internal structures when we talk about documents. In this lecture, most of them will be focusing on coreference. That's why your reading is about coreference. And we cover a little bit about discourse parsing and a little bit about sentence element prediction. So the first document problem, entity coreference. So we say in sentence level, we detect all the entities, named entities, and then by going to the document, we now can see what's the relation between all these entities. Here are one example from this paper. So to do document level entity coreference, the first step, of course, is we need to find where are the entities. And entities, they are inherently, they can be, we can use the entity level, we can use a sentence level entity classifier to find the entities for us. However, it's not enough because NER right now is normally only work on named entities. For example, country names, person names. It doesn't work on all noun phrases. As in this example show, we underline all the noun phrases in these two sentences, like the speech therapist. You probably won't detect that in the NER system. So the first step is a little bit more work you have to do after NER. Second step is that we cluster all these noun phrases to create groups so that the same group of entities refer to the same underlying word entity. The same group of mentions referring to the same underlying word entity. So the word mentions and noun phrases will appear a lot in this lecture, and they are kind of the same in this context. And entity is the combined cluster. So by definition here. So noun phrase detection. A lot of people think coreference is just a simple classroom problem. Noun phrases are, a lot of people just develop a coreference system using predefined noun phrases or using given noun phrases. But however, noun phrase is actually a very difficult part for coreference systems. We'll cover this a little bit more at the end of the lecture. But right now, I'll give examples about why noun phrases can hurt coreference performance by a lot. Using the same sentences, if we detect a noun phrase correctly, we know that this is a therapist. But if we detect a noun phrase incorrectly, we are going to say the noun phrase here is a speech. This will change all the decision you made later for coreference. So this upstream task will have a lot of effect on later tasks. But nevertheless, most people still do this as a pre-processing step because it's not very trivial to combine noun phrase detection and coreference. We will cover one model in this lecture about how to do that. A coreference model, apart from the noun phrase detection, is a very traditional machine learning model. Just like any learning model, we have these components. We need to define what are the instances. We need to extract relevant features for each instance. We have to define our evaluation metric, and then we need to know how to train it. Or in structured prediction world, we are more interested in how to search the correct structure. Today we cover the first 3 points. The last part is search algorithm. I think the lecture will be given by Dan later, not in this lecture. So let's look at instances first. So coreference itself is structured prediction problem. All you need to do is, given like n different entities, you have to put them into groups. There are actually exponential number of possible grouping you can have. If you are listing all the different grouping and extract features from them, ranking those, that will be a very difficult task. Basically intractable. So models are designed to approach this problem, basically to search and reduce the space. People simplify this by always making pairwise decisions. Not always, mostly making pairwise decisions. Given the 4 entities we extracted from the previous example, the question is, what will be the red entity linked to? Which mention he wants to link to? That's the way of constructing instances. So it becomes a classification problem at this point. If we look at the three previous entities individually. So we have, in this lecture, we're going to talk about 4 major models about making instances. There are actually a couple more more than this, but these 4 are, I think, the state of art for some time and quite important. The first model is the simplest one. It's called the mention pair model. All you basically do is to construct all pair of mentions. Between every pair, you say they're coreference or not given the gold standard. If the answer is yes, you have positive instance. Otherwise, you have a negative one. So this is very simple, but there are many drawbacks to this model. The first is you have a very high class skewness. You have a very few number of positive instances and have a large number of negative ones if you get all the pairs from a document. Like for this example, when you take Queen Elizabeth and you pick all the previous, I'm not looking backward in this example. Actually, you should look backward, but let's look forward here. When we take Queen Elizabeth and look forward for all the mentions, only one of them is actually coreferent with it. All the other one are negative examples. So this is hard for training, definitely. And second, it can have a lot of conflicts when you make individual decisions. For example, when you make a decision that 1 is coreferent with B, 1 is coreferent with 2, and 2 is coreferent with C, but 1 is not coreferent with C, and you have a problem of which one do you trust, which classifier do you trust. It's not very trivial to solve that problem. Other problems like that's not obvious may include it cannot capture cluster level features. So an entity is normally formed by a cluster of 4 or 5. Within the cluster, you may have some features internally. For example, if the cluster is the whole cluster about a person, is the whole cluster location cluster or something like that, these features are actually useful for deciding coreference, but they cannot be captured by a mentioned model, a mentioned pair model. The fourth drawback of this is that there's no ranking of instances here. All these instances are treated equally, no matter how. So, given that there are so many problems, but it's simple to implement, people later invented new models based on the mentioned pair model. There still is a pairwise model, but they replace one part of the pair into entity. So now we have an entity mention model. When they write entity mention, they say the entity is before and mention is after. That means we always pick a mention and we look backward and look for an entity. So in this way, we create instances between the mention and the previous cluster. And the previous cluster is actually formed by previous decisions. So that means you are growing, when you're reading from left to right or from top to down, you are growing your entity clusters larger and larger. And for each new mention, you are going to decide whether I want to join a previous cluster or I create a new one. In this, normally, so we follow a natural discourse level because discourse order, that's how humans do this, right? In this way, we can use partial clustering features. So here are some example clustering features that people find useful. Whether the whole cluster contains entities that have the compatible gender. For example, the gender, you can infer the gender from a noun phrase. You can infer the gender from pronoun. And you combine them to see whether they are all compatible. And second, whether it's the cluster containing only pronouns. So a cluster containing only pronouns is actually problematic. So in a natural language, you don't start talking about he without mentioning who he refers to. So it's normally an error when you have only pronouns in a cluster. You want to still find one antecedent for all these pronouns. Whether most of the entities are in the same gender. This is actually a very cute feature. I don't understand how people define modes here, but they define modes here in many different ways. So now so I'm not going to talk about how people define modes, but I will talk about other ways to overcome this. Basically, how to overcome problems about cluster features, because modes is not a very precise word to follow. And maybe the size of the cluster. If the cluster is too large or too small, that might indicate something. These are cluster level features. The problem of an entity mention model is that there's still no ranking between the antecedents. So given the mention, there are 3 clusters before you. Which cluster is more important, we don't know. So this is a ranking problem. And then cluster features are actually hard to design. Like most of the entities are female. That's a very hard to define feature. So people also go all the way around, all the way to like entity features, entity models. So we start from mention pair, and we go to entity mention model, and people even go all the extreme to entity centric. They don't even look at mention at all. They treat everything as entity. So that's called entity centric model. So entity centric model is a thing that you're basically directly evaluating which partition is correct. So you are comparing all the different partitions. As we just said before, all the different partitions, there are exponential number of partitions. So evaluating all the partitions is actually intractable. So when people doing this, they are doing heuristic search or other things to approximate that. Actually, the process is very similar to before. People still build up clusters during learning, doing from left to right. However, the problem right now is we don't have cluster creation gold standard. We don't know which cluster to merge first. So given the final cluster, if you you only know the final cluster, but you do not know the path to reach the final cluster. You can merge 1 and 2 first, or 2 and 3 first. The gold standard is missing in this part. So either you can create some gold standard on your own, which we can see some other people do that, or you train it with some other methods. So in this Clark and Manning paper, in the reading list, actually train it with Stagger, which Graham talked about a little bit before, in order to deal with this training and test problem. We always mention about ranking. We say there's no ranking between the instances. So naturally, we have a ranking model. So the ranking model adds relevance, relative importance to previous entities. This is useful because it has something called EC first intuition, has been proven to be very useful in parsing and coreference. Is that when you pick the easiest decision right now, it's easy. You'll probably get a better clustering outcome at the end. So EC first, you can rank your instances based on EC first intuition. Also, the ranking model helps to deal with imbalance between positive and negative. So although you have only one coreferent antecedent before you, the ranking allows you to create ranking pairs. So you have one positive and 5 negative, for example. You put it into one ranking list. A lot of ranking algorithms actually look at the differences between the positive and negative. In that case, you have a lot of, you don't have to deal with the imbalance problem yourself. For ranking models, you have a small problem about anaphora. Well, anaphora is a little bit subtle definition we discussed on Piazza today. So basically, anaphora, simply speaking, is to find whether a mention had something to link before it, to have to something to ground in the previous context. So anaphora problem here is to define whether a mention is anaphoric. When we say anaphoric, it says whether a mention have antecedent or not. If it is the first mention of this cluster, then it does not have an anaphoric mention. So anaphora problem is you can't deal with it in a naive way, in a naive ranking model, because ranking only take the positive and negatives and put them on the rank list. But it's actually very simple to do that. Oh, okay.
That antecedent should be within a sentence, or also can be.
Oh, normally antecedent, there's no restriction on sentence boundary. Basically, they are. So everything we talk here is does not have a sentence boundary. So a way to solve this is to add a null mention, or sometimes we call it a root mention in this. So if your ranking with the root mention is higher than anything else, then you can treat it as non-anaphoric. So this is a very simple trick to solve an anaphora problem. We have 2 different ways of doing ranking as well. Just like say before, we have mentions, we have entities. So we have mention ranking and entity ranking. So mention ranking, due to its simplicity, is the most dominant method right now. And I think the state of art is a mention ranking model. Basically, you rank previous mentions. An entity ranking model is to rank previous clusters, not individual mentions. This is a previous very important paper in Coreference. It's by During and Dan Klein. So what he do is a mention. Its basic idea is a mention ranking model. So from left to right, you have 4 entities. The A means is antecedent decision set. For the first one, you have no decision to make, so that's fine. When they say new, they make a new cluster for it. And the second one, you have one decision to make, whether you want to merge with the previous cluster or you want to create a new. And the correct answer is actually you want to merge with a previous cluster. So you label these 2 instances as one of the correct and one of them as error. And the third one, you actually want to create a new cluster. And linking to 1 or 2 are both wrong. So we have 2 negative examples here and 1 correct and the 4 is the same. So by doing this, you can create a rank list for each box. For A1, you have nothing to do. For A2, you want to rank the correct one over the new one. For A3, you want to rank the new one over the 1 and 2 hypothesis. So this is a not linear model. It's not a neural model. We haven't gone into the neural model land for now. The problem of this is there's no gold standard antecedent structure in training. Because this is a probabilistic model, so you can easily sum over all possible antecedent proposal here. So this is the entity ranking model by Vincent Ng. So he ranked previous cluster, just as we said. He also added a null cluster to its antecedent to make it to solve the anaphora problem. Oh, by the way, the new here is actually solving the anaphoric problem in the rest model. So the model here is they achieved the state of art at that time. However, they use a very complicated set of features. Here I only they are actually 39 feature. There are actually 39 feature templates to extract features from this. So it's a very complicated model to reproduce.
So it seems to me that entity ranking models are a superset of mention ranking models. So this is strictly more expressive than a mention ranking model, I think.
Yeah, I would agree with that. Yeah.
But mention ranking models are simpler, so people
Yeah.
decide to use them.
I think it may be also be that mention ranking models are easier to train in many cases.
Okay.
If like more expressive models are definitely harder to train.
Okay.
But another reason is that like when Vincent do this is 2009, it's earlier, and if you implement an entity ranking model, it may work well, but I'm not sure because there's one other model which is a little bit difficult to put into mention ranking or entity mention model. It's called Latent tree model. My feeling is that's very similar to mention ranking, and somehow is that the process is that it will create a tree during the process of reading a document. It first creates a root. For each new mention, either it connected to the root or they connect to another mention. So after that, you will have a tree. When you read off all the subtrees under the root, you will have the clusters. The problem of this is still the same. You don't have a gold standard for a tree. The gold standard you have is only the final cluster. So during here, they call it latent tree model because the gold standard is actually latent. So how do they derive the gold standard tree? Is that at each stage, they will use the current feature to rank all possible gold standard trees, and to find the gold standard trees that has the highest score given our current feature configuration. So basically, it's saying that I pick a tree that I think I can decode the best, right? Among all the trees, if the tree gives the highest score, that means it's easiest for my current model. So they are picking the easiest tree here. And then they find the tree differences between the two trees and do the training. This is a not very easy to understand model, in fact. And I trained this model myself. It's not very stable on some data sets when you are not careful about some small decision like type breaking and stuff.
What's the difference between decision tree and this model?
Oh, wait, so decision tree is a learning algorithm, a classification learning algorithm, right? So this is the search tree. You are searching your answer. You haven't done anything about classification yet. So one instance here is a tree, right? In decision tree, one instance is a thing, and you create a feature tree. Right now, one instance itself is a tree. And then you're comparing the structure differences between two things. You can imagine it's like something like parsing. You parse it to a tree, and you compare whether your parsing is correct or not. But in this case, you don't have a gold standard parsing. So what's the role of neural network here? That's more about what we care about, because this is a neural network for NLP, not introduction to NLP. Let's revisit the problem of coreference. We have instance problem, we have feature problem, we have metric problem. I haven't talked anything about metric, but we have a metric problem.
I have a question about mention ranking.
Okay.
So where is the clustering component in mention ranking?
Okay, so I skipped that a little bit. So in mention ranking, basically, for example, this is one mention ranking configuration, right? At each stage, you are going to decide one of the action you are going to take. You can actually recover your cluster based on your decision. For example, at the second stage, if I decide to create a new cluster, then I would take new. It will actually create a new cluster for that. When you just, all you need to do is merge a decision of all these boxes.
So this results in you getting a tree, actually, doesn't it?
Yeah.
So the idea is it's a tree where the root is the first mention in the tree, and then everything after that can point to either of the elements, and then everything that is pointing to that eventually travels to the first mention is clustered together.
That's why we said like latent tree is very similar to mention ranking. It's only that latent tree doesn't do any explicit ranking, so we don't say it's a mention ranking model. But the way of constructing things is still a tree, right? That's also the case why we say the mention ranking model does not have a gold standard for of the decisions, because you don't observe the tree. All you observe is the final cluster. Is that clear? Kind of.
How do you score? Is it is the total score of the tree the sum of all the arcs?
Oh, yeah, I haven't really covered scoring here. So it's your choice, basically. But in these models, yes. Every score is just the sum of all the arcs. In principle, you can also have cluster level scores, which look at multiple mentions and give them a score.
The problem is the score of each arc is fixed, right?
The score of each arc is fixed according to...
If you have mention ranking, like the relations in between these two words are like fixed, like.
The features are fixed, yes. But the feature score is updating during the training. So you will have different... When you have different weights, you will have different proposal. So here we only talk about search. So I think the problem is that we haven't discussed anything about learning. So everything we've done here is just creating instances. Given the instances, we extract features from it. So the features might be on the arc, or it might be on the whole tree. We don't know. It can be anything you decide. And then we get a score for the whole instances, and we feed it to a traditional, any learning method we have to solve the problem. So we only cover search here because learning is not so different from the other way, from the other models. Perhaps I have to. It's better to do that before. So yeah, any question before we jump into a little bit about neural network stuff here? Okay. Yeah, we have 3 problems we just said. So for instances, we have created a lot of ways of creating instances. We either create trees, we create pairs, we create clusters. There are all different ways of creating instances. For features, we show that some papers use a very complicated set of features. Like we have 39 feature templates from Kuhn's paper, and this, I don't know how to read his name, Bjorkelund and Kuhn, maybe. They use actually they extract a lot of features first, and they use a feature induction, a standoff feature induction technique to induct that using a decision tree first. And then finally they select a lot of features and then put into their final model. So these are all very hand engineering and very time consuming. A lot of part of this can be replaced with neural networks nowadays, because neural networks are supposed to be feature extractors, and at least we hope them to. Now I want to cover something before neural network is that is error-driven analysis. Graham actually talked about this last lecture. The people there to conduct error analysis for parsing, the same group of people actually. I'm not sure about the first author, but it's Dan Klein's group. They do another analysis for coreference as well. So let's see what kind of errors could appear in a coreference system. So this graph showed that how they could change a system cluster, arbitrary cluster, to a gold standard cluster within 5 steps. So given any clusters, they first correct all the mention spans, so to make sure all the mentions are correct. And then they split large clusters, and then they remove incorrect mentions, which like some mentions that even they are not mentions, but system might think is mentioned. They remove this wrong mentions, and they introduce new mention that's not discovered by the system, and then they merge small cluster into large clusters. So given 5 steps, you can transform any system cluster to a gold standard cluster. So the error types are definitely happen in any one of these places. So the error could be one of them goes wrong, or 2 of them goes wrong. So it would be 5 plus 1, 2, 3, 4. They would probably be 9, but they only have 7. I don't remember which one they don't use. So they finally have 7 different errors here. Span error, conflated entities means you merged different clusters together. Extra entity means you have extra mention means you have extra mentions. Like look at all these errors. They analyze all the system they can get and find out their errors. So let's remember this graph for now. We'll revisit it later. So after doing the error analysis, Dan Klein's group find out that you don't really need to design all that many features to do coreference. So they call it, they have a paper like a very important paper called Easy Victories and Uphill Battles for entity coreference. So they say using surface level features, simple baselines, they can beat like all the state of art, and the actual uphill battle is on the semantic side that no one can solve. So they don't solve in this paper. What they propose is still a mention ranking model. As is very popular. They design their objective to be different error types. So we have 7 error types we just talked about. Here they use 3 of them. Whether it's a false anaphora. False anaphora means you should have connected to something before, but you didn't. False new is you shouldn't have created a new cluster, but you did. And wrong link, basically connect to the wrong clusters. So note that they don't consider anything about mention span, only coreference linking errors. So there are 3 different coreference linking errors. The combined loss is just the loss of each one of them. They have 3 hyperparameter to tune here. It's very hard to tune, but they finally get it done. It's very impressive. So why they say easy victories? They say this is easy victories because they only use surface lexical features. They ignore They ignore all complex features and replace all of them with surface features. Here are some examples. Most of the previous system will have number and gender compatibility feature, whether the number are the same, whether they are both plural, or whether they are all female. Here they say that this can be encoded by the pronouns and by the form of the word already. They don't really need to design a feature for that. There's also a feature that's widely used before. It's called centering feature. Centering feature is that when you have 2 sentences close by, if the 2 verbs are the same or related, and the subject of that verb must be coreference of some, the subject of this must be coreference, and the object of this not must be. might be coreference. So this is the centering theory feature. But however, when they add the verb into the feature set, they said this can totally help them ignore the centering theory features. And another example is definiteness. Whether you have definiteness marker before word, all you need to do is just encode the previous word before the mention. You don't really need to, or the first word of that mention. You don't really need to do that. There are many other things happens. Here are just some examples. The results, this is the final list of their feature templates, much smaller than the feature template designed by Vincent, but still quite a lot. This is the final feature set. Number of actual features are numerous, but the feature template has been reduced by a large amount. However, we are still not satisfying because we want to do automatic feature extraction. We don't want feature tables like this. But we already said that a lot of them can be captured by lexical features, right? Neural networks are the best for capturing lexical features. We have embeddings. Any lexical matching is not good, as it's not comparable to embedding matching, right? So this gives us a hope to use neural networks for coreference. So here are some other possible improvements with neural network. We can train towards the final metric. We haven't talked about it, but it's obvious because the metric is hard to compute just like any other NLP task like BLUE. We can use deep reinforcement learning. We can learn the features from embeddings because a lot of them are lexical. Actually, they can be better captured with neural network than normal lexicalized feature. And one more thing is we can train a full system to reduce more error types. The Dan Klein's paper is really nice, but it still considers only 3 types of error, but they analyze 7. A lot of the unanalyzed errors are mention errors, mention span errors, create false new mentions or missing mentions. These 3 error types are not considered in the previous paper. If we can do an end-to-end neural network, considering all the mentions, we can include all these error types. So 7 error types, if we can cover them all, that would be the best.
Give a specific example of how does the loss function deal with certain type of error?
So actually, the loss function is very simple. So false anaphora is just counting how many false anaphora given to different configurations. False new is just counting how many false new you have made. So we are comparing 2 decision set and calculate the number, row count of this. And then we multiply the row count with some interpolation parameter, a hyperparameter they chose from. I remember it's 0.5, 0.2, 0.2, something like that. But they research to get the number. And the final loss is just a sum.
And so they adjusted the alpha to get a higher score on their final evaluation.
Yeah.
Right?
Yeah. So it's actually a very hard to tune process. They tune it successfully. It's pretty good. Yeah, we can train a full system to reduce all these error types at once. So that's the possible gain from neural network. Let's see how people, actually there are papers related to each one of them. The first one, Mr. Clark and Manning paper, let me see. Oh, I have animations, cool. Hey. I think something wrong with the animation.
Wait,
Oh,
it's just taking time.
okay. I'm just pressing too fast.
It's strange.
Okay, I should stop here until it loads. Terrible animation, but
Shall we switch to the?
well,
The other
maybe I
slides.
think it just slow.
There we
It
go.
comes out.
Okay.
Okay. So this is one attempt to use neural network for coreference. So basically, it's a mention pair model. Wait, it's both mention pair model and cluster pair model. They actually pre-train a mention pair model for the system, and then they feed it to a class pair model. So here's how they work. For each mention pair, they train a feed-forward neural network, and that one is connected to the cluster level representation. For these two clusters, they are picking all the possible combinations from these two clusters, all the mention pair, and they stack it into a matrix, and they do a pooling to get a final class pair representation. So this is trained end-to-end from both cluster and mention pair model. The features of this, which is listed there, a lot of them are embeddings. Some of them are still hand-designed feature. For example, here and document features. So the way they do this is that the first couple features are mostly embedding features. The last few, some of them are very hard to return to embedding. For example, the distance between two mentions, they write it as one hot vectors and append it to the whole feature set. The training algorithm, the training loss is still the same as the direct one. Alpha, the three different loss combined by alphas. So here, what they want to do is a cluster level model, because you can see they have cluster pair representation. So we still have the problem of which two clusters to merge first. It's unknown because the reward is only at the final. We only know the final coreference. Then when we say something about reward, we immediately know you can do something about using reinforcement learning. So they actually train a policy network. The policy network is deciding whether two classes are merging or not. Basically, the action is just merge or new. Merge or new, I think. Work. Okay, let me see. So they continue to improve that previous method by introducing a little bit more about reinforcement learning to capture the evaluation metric. So the previous slides, we still say they're still using the direct and Klein hand-designed loss function. In this paper, they are using the actual evaluation metric used by Coreference, actually B cube, one of the 4 evaluation metric here, one of the 4 main evaluation metric for Coreference. They actually find that their reinforce doesn't help much. The best is called a rewards rescaled reinforcement methods. For details, we have to read the paper. We don't have time to cover it here, but it's typical that reinforcement learning are very hard to apply to NLP problems. Another example of using neural network to capture features is to use neural network to capture cluster features. If we still remember something we talked about earlier about most mentions are female, that kind of feature is very hard to design and not very precise. In this cluster feature neural network, they actually, for each cluster, they run an RNN of all the mentions in that cluster to get a cluster representation of it. This is actually quite similar to the Manning way, where they cross any two, they do a cross product between two clusters. However, here they can use RNN to capture single clusters by themselves. This actually can somehow capture most features and all features phenomenon. They've shown this by plot their cluster representation at the end. in this graph, actually each different color represents somehow different characteristic of the mentions. Some classes are about pronouns, some classes are about locations and whatever. And this one is the end-to-end neural coreference. I think it's the new state of art right now. The two main contributions by this paper is that first, can we represent all the features with a typical neural network? And then whether neural network allow us to flow the error from top to bottom. So this solves another type of error, is the span error, which is never solved before. To solve the span error, that means you have to jointly learn span detection, mention detection, and coreference. Their joint learning way is actually they're doing it really brute force. They just pick all possible mention spans in a document and then throw it to the next layer of neural model. By all mention pairs, basically to construct all the mention pair, you need to pick a start, you need to pick an end, and then the number of mention pair you can have is actually length of document square. If the length is v, you have v square of possible mentions. This is like a square doesn't sound bad, but it's still quite unacceptable. But in fact, you don't really need to do that. You don't have mentions more than 7 words long. If you don't have more than 7 words like mentions in a document, you don't really need to do that. So actually, they use a threshold as 7 to do that. So they build mention, and then they use a couple trick to filter out mentions in the first place. So the mention size is manageable. And then to do quite standard things. For each mention, they capture the mention representation. What we have to focus here is that they use the experience before. We say that the first word of the mention, the previous word of the mention, the last word of the mention, the next word of the mention, they are all important features in coreference. They build all of this into their mention model. One more important feature about mention coreference is the head word. When we want to decide whether 2 mentions are coreference, the more important word is the head word instead of all the other words. For example, if you still remember the therapist example at the first slide, the speech therapist and the speech are quite different because the head word is different. One is speech and one is therapist. So in order to detect head words, normally people use dependency parser to extract a head word. Here they want to try it to do it all unsupervisedly, not unsupervised, want to do it all neural networks. Don't use any parsing feature. So here they use the self-attention to pick the head word. They're assuming that the self-attention word, the most attended word, is most likely to be the head word. And we'll see how this performs in the later part. In this part, we have built a mention representation for a span. You can look at that. For example, we build a mention representation for General Electric. Now we fit this mention representation into a cluster model. This cluster model is basically a multi-layer perceptron, and making a single decision at the end, whether it's true or false. Everything is the other setup of this model is exactly the mention ranking model, except that the way of how they extract features. So let's look at the so they said the quality of their mentions is actually pretty good. When they change lambda is the weight of filtering mentions. They say when they change lambda, they have a curve of that, which reach the best previous mention extraction system, the red dot here. The red dot is on their curve. So in their model, they can like freely choose more mentions or few mentions for. Well, it means that the curve is kind of optimal right now. What is interesting is their ablation study. Most of their features are less equalized. A couple of them are not. First one is distance. it's very hard to do embedding for distance. The second one is the speaker information. These are some metadata in the document. That's really hard. Basically, there are some data sets that contain speech. It's basically Hector says something, Graham says something, and you have the speaker label on each sentences. These are pretty hard to be captured naturally. Say they use an additional speaker feature. What we can see interesting here is this head finding attention, which is to use self-attention to find a head. Without the head finding attention, the performance actually drop a lot. There are the different embeddings, which not very interesting. Let's revisit the error types we talked about before. When we look at the error types that they analyze, the majority of the error, actually, you can see the span error and missing mention are a very major source of error in almost all the systems, especially missing mention. It's like one of the major source of the top performing system. So that's why doing this end-to-end span-based coreference system help a lot in the. Okay, so I think we have finished the coreference part. We have a little bit more time. We're going to briefly talk about the other part of document level models. They are actually related to entity coreference in some extent. So one of them is called discourse parsing. It's basically you move parsing to discourse. You have different set of formalism. You don't have pantry bank, but you have another different type of tree bank called DST. And your units are not words, but phrases, clauses. They call it EDU. I don't remember what EDU is short for, but whatever unit. So they are parsing a piece of text into relation between discourse units. Of course, it's discourse unit. Most researchers mainly using this called IST style discourse parsing, which is shown here. The early work about using neural network for discourse parsing is actually very similar. Basically, a kind of a copy of the parsing model by Richard Socher on the discourse land, a recursive discourse parsing in a CKY style. And later, people have invented like more sophisticated method, like hierarchical LSTMs. Basically, they use the first LSTM to capture. Let me remember. The first is used to capture each discourse unit, the EDUs. The second LSTM is to capture the representation of multiple EDUs. So they made a decision of whether the EDUs should be merged and what is the relation between two EDUs. Discourse parsing, although it's not very popular in NLP because it's probably hard to do, but it's still people shown that it can help represent documents. Just like in sentences, there are a lot of people try to use recursive trees to represent the meaning of a document, of a sentence. People also try to use recursive discourse trees to represent the document meaning. In this year's ACL, Noah Smith showed that by incorporating discourse parsers, you can actually do sentiment classification or topic classification better than before. This is already covered by Graham in the previous lecture, GAN lecture, that to predict the discourse connector between two sentences. This is you can think of this as a shallow discourse parsing. You don't need to construct a full tree, but you only need to decide the relation between two clauses. One thing I really want to talk a little bit about, so I rushed a little bit over the discourse parsing, is discourse prediction. This is a very simple idea and very simple not very simple task, a very simple configuration task, but the task itself is difficult. So in document level, we don't do language models, we do discourse unit predictions. Language model predict you the next word. Discourse unit prediction can predict you the next sentence, the next phrase, the next event structure, whatever, or the next entity. there are two different, there's some different tasks on this. For example, reference prediction is to predict which entity you are referred to. This is very similar to entity coreference. Or the story corpus is asking you to complete the story given the first 4 sentences. So predicting discourse units can be think of as just a discourse document level language model. Let's look at the example here. Kevin is robbed by Robert, and if we look at the Z arrested X, we're going to predict what Z and X are. For humans, it's pretty easy to know that Z is actually, Z is most likely to be the police. If we know that Z is police, where is X? And X is most likely to be Robert. You won't say Kevin. And if Z rescued Y, and Y will be Kevin. So this is the discourse prediction thing, and it's kind of useful for entity coreference. So Pichota and Mooney use like straightforward RNNs to predict the next event. By event, that basically they say rescue X. They call this group as an event. And Peng and Roth in 2016, they introduced something called semantic language model. What they added to the Pichota model is they add discourse connectors. So Kevin was robbed by Robert, but the police mistakenly arrested him. When we have a but in between these two sentences, the meaning of the whole thing just changes. Now Tim actually referred to Kevin, right? Not Robert anymore. So they added a little bit more information into this discourse sequences so they can make better prediction. So they apply these two models. They train basically to train a language model, and they apply it to coreference and semantic parsing. Both improve the result. It can be think of you are doing just like in the previous work we have seen before. For example, in automatic speech recognition, you train a language model. It helps you to predict speech better. Now you train a discourse language model, it can help you to do coreference or parsing better. The story completion task is a kind of a different flavor, but very similar. It gives you the 4 sentences before and give you two choice or maybe 2 choice and asks you to find the correct choice. So this task is I don't think it's not fully challenging because some people have shown that only using the last sentence is actually very helpful in predicting the answer, which making it a little bit less interesting. They have a paper called Predicting the Story by Focusing on the End. Nice framing, but all they do is just looking at the words in the last sentence, which make the semantic flavor of this task a little bit weak. But still, it will be a future direction of interest. So the reason of this course, I think, is clear. A normal language model can help us predict the next word. Very useful for speech recognition or translation. And a discourse language model can help us predict the next entity, next event, and potentially useful in information extraction. People have already applied it on information extraction. They can probably be useful to entity coreferences. This whole lecture is about entity coreference, basically, and I hope that discourse language model can be applied there. So it's not actually fully applied to coreference land yet. Peng and Rolf do some experiment in 2015 saying that they can solve hard coreference problems using discourse language models. However, when they add it to their own UIUC coreference resolver, they haven't improved the baseline by much. So there's still some gap about applying this discourse language models to actual coreference problem. There's a very interesting thing, if you're interested, called the Winograd schema challenge. A lot of them require very difficult human semantic interpretation. For example, the robot case we have already seen, and the first example is old students were bullied by the young one. So when we change the verb, we are changing the coreference decision of them. There's a whole collection of this kind of sentences by the challenge. And it's very interesting to see whether semantic LMs can help solve this. This is basically an unsolved problem right now. I think that's it. Any questions?
I have a minor question. So when you're discussing an opera, you had a slide that basically said if you can't find the antecedent, then maybe you have like a null pointer or something along those lines.
Yeah.
So a few times I saw in the reading and in the presentation that there's an assumption that if you had, for example, a pronoun, it refers to a noun that came before it. Do all the models work just as well if it's reversed, if the pronoun comes first and then the noun comes after it, or do the models kind of break? I know it's uncommon, but it still happens to me.
Yeah, I haven't done any experiment on that. I can only say my own. So I mean, the common thing is to link a pronoun to a noun. So when for example, you are saying you have Clinton and he. When you reverse them and you want to link Clinton to he, is that the
if
question?
the pronoun comes first, and so do all the models assume, either the models assume that the noun comes before, or the models are indifferent to whether the.
So they do assume something. It's not easy to say what exactly is they assume because there are multiple antecedents before at each decision, right? Normally, the model, if trained correctly, it will not try to connect it to a pronoun. If there's a Clinton here, and the first mention is a Clinton, the second is he, and the third is also Clinton, it's very likely that Clinton is linked to the first. And they also can reach to the correct answer. So if you only reverse two of them, it might not hurt the performance a lot. So because it's a joint decision of multiple antecedents, right? I would say that the behavior will change. It will tend to pick the easy one because they always have this easy first intuition. If trained correctly, that's the way. However, if you have a case where he is the first place and the second one is, for example, Clinton, and the he is like kind of unbounded, it's very hard to say. I would say the performance will be worse, a little bit worse, because when they extract the features, most of them they really care about the direction of the feature. If you create features saying that you don't care about the direction, then probably not. But when people design features, they normally care about directions.
So they normally assume that it goes one way.
Yeah. Yeah. So actually, all the Coreference system right now always look back. Very seldom they look forward. The major paper I discussed here are all looking back. There might be papers looking forward. I haven't read them a lot. I mean, it seems that it's not necessary to look forward.
So I have a question. One of the obvious applications of co-reference is question answering or machine reading or something like that. Do you know of any work that either uses co-reference or maybe trains co-reference using that?
I know there's one, definitely work on both. I know a word for question answering during the literature search. I don't remember the title, but there's also one for, there's a one for squad test. But the conclusion is that the coreference helped them to reduce the distance between the entities.
Okay.
So it's not that the coreference itself gave a lot of mention. It's that the structure that reduced the distance so that neural networks are easier to train.
Okay, but it still helped. Right?
Yeah, it still helped.
Yeah, so that makes sense.
That's an interesting discussion by Chris Dyer about how linguistic structure can help this, right? So they said that it's more about the distance instead of the actual structure. So.
Right. So if you use co-reference, you make it easier for your neural network to learn, which is one of the big advantages of having.
Yeah. That's one done by LTI students on Squad.
Oh, great.
Yeah.
Okay. Thanks a lot. Let's give Hector a hand.